Okay, we're ready for review 3 over chapters 6 and 7. Again, click on the homework tab, and all the practice exams are way at the bottom. The first 4 in here. We're doing the third one today, practice exam 3, chapters 6 through 7. 25 questions. Okay, first says, find the area of the shaded region. The graph depicts standard normal distribution. Okay, so mean is 0, standard deviation is 1. Let me open up a calculator. This first problem could definitely be done easier with a calculator. This graph has z negative 0.98 to z 1.22, so we want to know the amount of area or probability within these two. There's a function in the calculator that'll do that called normal CDF. And it's found under second vars. As soon as this calculator turns on. Okay, so you go second and the vars button. And we never use normal PDF, so it's always either normal CDF, the second one, or inverse norm. Normal CDF will take 2 z-scores and turn it into an area or probability. And again, some calculators, you're already on the screen where it says normal CDF and you type the numbers in. Here I'm going to put them in. This is a little more user-friendly. Negative 0.98 was the first z-score on the left. And the right one was positive 1.22. When you have a standard normal, the mean is 0, standard deviation is 1, so we don't have to change those two. And then paste. And again, other people's calculators, you'll type, once you select normal CDF, a parenthesis will pop up, and you just have to type negative 0.98, comma, 1.22, comma, 0, comma, 1. So some of them you have to type all the information in, knowing the order, and others it's a little more user-friendly where it tells you the order. Then you got to be real careful on a test, answering to how many decimal places they want. It changes even from problem to problem. This one says round to 4 decimal places. 7252. 0.7252, and that's correct. So normal CDF will find you the area between 2 spots. The other function in the calculator is that inverse norm one. That's what this problem is for. It's exactly the reverse. Now we have the area given to us. That was the answer to the last problem. Now it's the question in this problem. They're giving me an area of 0.2451, and they want to know what z-score is here. In number 1, they were giving me z-scores and wanted the area. Now they're giving me area and they want the z-score. So inverse norm will do this. Second vars, go down to inverse norm, and as long as the area is to the left, you can just type it in. This area is shading to the left, 2451. 0.2451. If they want a z-score, then that automatically means you have a standard normal where the mean is 0 and the standard deviation is 1. Paste it. Inverse norm. And then again, how far do they want it rounded? Round to 2 decimal places. Negative 0.689, so we're going to make the 8 become a 9. Negative 0.69. Negative 0.69. And that one is correct. Now, what happens if the shaded area goes to the right instead of to the left? We've got 0.1423 to the right. Well, inverse norm needs to the left, and if you've got 14% on the right, well then 1 minus that's on the left, because they're complements of each other. So the easiest way to do to the right is, when you choose your inverse norm, I literally just type 1 minus point whatever the decimal is that's given in the problem. There's 0.1423 to the right. 0.1423. So 1 minus that would be about 85%. If there's 14% to the right, there'll be about 85, 86% to the left. So that way you don't have to actually figure out what it is exactly. You can just type 1 minus whatever it is. And that's what turns it around from going the wrong way. 1.07 if they want 2 decimal places, Round to 2 decimal places, 1.07. And again, that means you're 1.07 standard deviations above the mean. That's what a z-score is. Now, you can also do this if you want a raw score. Find the area, but instead of z-scores, now we have raw scores. This is from an IQ test. Scores have a mean of 100 and a standard deviation of 15. As soon as you hear that, you know it's not a standard normal anymore. We really do this the same way. We want 105 or less. So it says find the area. That takes me back to normal CDF. I only use inverse norm if I'm looking for a z-score or raw score. If you want to find area or find probability, use normal CDF. If they only give you one number in the question, then you can use negative infinity or positive infinity for the other number. Really, this one wants from negative infinity all the way up to 105. Well, I can't type negative infinity in here. This is the calculator's way of typing negative infinity, -1 E99. I usually just type negative 10,000. That's usually good enough, big enough to be considered negative infinity. And then the bigger number would be 105, but then we have a mean of 100 and a standard deviation of 15. So when those are not 0 and 1, you have to put them in. Paste. And now the answer to 4 decimal places is 6306, because this 5 will get bumped up 1. 6306 if they want 4 decimal places. 6306. Here's another one. It's going between 108 and 130. What's the probability or area of getting a IQ score between 108 and 130? So if there's 2 numbers you're going between, that's like problem number 1. Normal CDF, 108, 130. We don't need to use infinity or negative infinity when there's 2 numbers given. IQ scores have a mean of 100 and a standard deviation of 15. 108 to 130, 115. So the probability or area in this region would be 2742. The 1 would get bumped up to a 2. 2742. Round to 4 decimal places. 0.2742. Okay, here's one. Now we're reversing back to inverse norm because now we want to know x, the raw score, and we're given the area. 0.97 of the area is to the left of this raw score. What raw score is located there? What actual IQ score would somebody have if they were better than 97% of IQ scores? And this, notice this area is going to the left. So in inverse norm, if it's going to the left, you just put in the percentage or decimal, 0.97. But then if it's an x you're looking for, not a z-score, z-scores you leave this 0 and 1. If you're looking for x, a raw score, then you put in the mean and the standard deviation. Mean of 100, standard deviation of 15. So this will convert it to the raw score, and it'll give me an actual IQ score that's bigger than 100. 100 is average, so if you're ahead of 97% of the people, this should be above average. Somebody with 128 IQ would be ahead of 97% of people. Round to 1 decimal place. So you got to be real careful because they switch a lot. 128.2. 128.2. Well, what if it's 97% to the right? Well, again, if it's to the right on inverse norm, the easy fix is when you're putting your 97% in, do 1 minus 0.97, which is literally 0.03. If there's 97 to the right, there's got to be 3% to the left, because all there is right or left. If it's IQ, the mean is 100, standard deviation is 15, and then we'll get x, the raw score. Here's somebody who's only ahead of 3% of the people. 97% are ahead of them. So they're going to have a very low IQ score, and they only have a 71.8. If it's rounded to 1 decimal place, 71.8. So that's a pretty low IQ score. Okay, so now we can apply this to a practical problem. It says, assume human body temperatures are normally distributed with a mean of 98.2 and a standard deviation of 0.64. A hospital uses 100.6 as the lowest temperature considered to be a fever. So even if the normal temperature is 98, if you're below 100.6, then they say, okay, maybe you're a little warmer than normal, but you don't have a fever. Once you hit 100.6, then they'll say, okay, now you have a fever and we'll try to treat you. So the question is, what percent of normal and healthy persons would be considered to have a fever? And does this percentage suggest that the cutoff for 100.6 is appropriate? Well, this is the lowest possible temperature to be considered a fever. So what percentage of healthy persons would be considered to have a fever? You would have a fever if you're at 100.6 or higher. So to do a number or higher, if we do normal CDF for this, 100.6 is the cutoff for fever, and then all the way up to infinity. So I would just put 10,000 for the upper limit. And then the mean was 98.20. And the standard deviation was 0.64. So the probability or area above 100.6, it says 8.84, and then notice the way at the end, E negative 5. This is again scientific notation that means you have to move the decimal 5 to the left and you'd get 4 zeros, 0.000088 on and on. So it's a very, very small probability. Another thing to notice is they want a percentage here in the answer. So you can turn a decimal into percent by multiplying by 100. And this makes it 0.0088%, so that's still extremely small. Round to 2 decimal places, well, 00 is the second place, and then the 8 would bump this up to a 1. So 0.01%, which is like 1 in a 10,000th. So what this is saying is 1 in 10,000 people are healthy, but it shows that they have a fever. Does this percentage suggest that the cutoff of 100.6 is appropriate? And this has a very small probability to it. And so the answer to this, the idea is you want to catch people that have fevers. If they really have a fever, we want to catch that and help to cure them. So since this is such a small probability, we're not going to catch those kind of people. So this would be no, because there's a small probability that a normal and healthy person would be considered to have a fever. Or, let me think about that for a second. Because there's definitely a small probability that a normal and healthy person would be considered to have a fever. So I guess this would be yes, because some of these are tricky, you got to read them a few times. It's yes because we don't want a healthy person to be considered to have a fever. So this is a good cutoff to where the probability is small, yes. So it's yes because the probability is small. It's clearly a very small probability, but some of these yes, no's, you got to read them and be careful which way they're actually asking the question. We don't want to catch people that are healthy and say that they have a fever is what's going on there. So the minimum temperature for requiring further medical tests should be what if we only want 5% of healthy people to exceed it? So here we had a very small number of people exceeding it. What if we wanted to get the upper 5%? The upper 5% exceeding this, what temperature should that be? That's exactly what an inverse norm is. Inverse norm will give you a score, a raw score. Now since we're doing the upper 5%, that's where you have to do 1 minus again, because the percent is actually on the right side of the graph. Inverse norm can only do area to the left. So by doing 1 minus 0.05, we're really getting 0.95. There's 5% on the upper side, but there's 95% on the lower side. The mean again was 98.6, and the standard deviation was 0.64. No, it's 98.2 and 0.64. 98.2. So if you have a temperature of 99 point, how many places? 2 decimal places. 99.25, that's the cutoff we'd rather use so that we get 5% of people that way. 99.25. That'll catch the upper 5% of people. Okay. Moving on to the next section, we move on to all the problems up to this point in Chapter 6. Never mention anything about a sample size. As soon as a sample size is mentioned, there's a giant concept in statistics called the central limit theorem that plays a role here. And we have samples of exactly 39 students here. So for you to apply the central limit theorem, and you must check for this anytime there's a sample size. In the first two sections of this chapter, we didn't have to worry about that, but now once you move to the third section, 6.5, then all the problems have sample sizes in them. So if there's a sample size, you need one of two things. Either they need to tell you somewhere in the problem that the original population is either normal or approximately normal. Many times they don't mention that, or many times they'll tell us that it's definitely not normal. Secondly, the other big thing that can help us is even if the original population is not normal, or if we don't know, as long as the sample sizes are greater than 30, then the central limit theorem will work. So because the sample size here is 39, so n is greater than 30, then what happens in the central limit theorem is that the sampling distribution, the one we're actually going to work with, we don't work with the population, we work with samples. The average of all these samples we take will be approximated by a normal distribution, even if the original one isn't normal. And the mean will still be the same as the original mean, but the standard deviation becomes the original standard deviation divided by the square root of the sample size. And it's not precisely a normal distribution, it's approximately a normal distribution. So this one is A, and that's right from the definition of the central limit theorem, the big concept in section 6.5. So you can use this then, the rest of 6.5 asks you to find probabilities, and it's very much like the early part of chapter 6. If you're looking for area or probability, you just use normal CDF. But when there's a sample size mentioned, you have to divide the standard deviation by the square root of the sample size. So part A says if one woman is randomly selected, I have a sample of 1, find the probability that her height is less than 65. So let me do this where we can see everything at once. Okay, so second vars, normal CDF, we want less than 65. So we want to go from 65 and all the way down to negative infinity. So you put the smaller number first, which is negative infinity, negative 10,000 for us. Then the 65. And then the mean is 64.6. So as soon as there's a sample size, that's going to always stay the same. 64.6. But in the, whoops, I put that in the wrong spot. 64.6. But then here's the tricky part. The standard deviation is 2.5, but anytime there's a sample size, you have to put 2.5 divided by the square root of whatever the sample size is. And when it's a 1, it's not actually going to matter. You don't even have to put square root of 1 if you don't want to. So this will turn out to be, really, when there's a sample size of 1, that's really the same as what you were doing earlier in the chapter. Round to 4 decimal places, 5636. 5636. But what if the same question happens, but there's a sample of 46 women selected? Well, I can hit second enter and call up the last statement I just gave it. And all I have to do is back up to the 1 and change that to a 46. But that's definitely needed here. And a lot of people on a test for these types of questions, they forget to put that square root of 46 on the standard deviation. 2.5 divided by the square root of 46. So notice it makes the probability larger, 8611. 8611. So watch out for sample sizes attached to probability questions. Then you got, and that formula is on your formula sheet too. I should pull that up too. If you go back to My Math Lab, go into Course Tools, Document Sharing, Remember, I have a bunch of extra resources here that could help you. There's review sheets, notes and examples, problem solving technology, how to solve the reviews and examples. There's the orientation that you should have read through everything before starting. There's another copy of the syllabus, and then there's this copy of the formula sheet that you get for all remaining tests. So this is exactly what you're going to have on the test. And the central limit theorem is right down here in chapter 6. Central limit theorem, standard error is another way to call the standard deviation of the samples is called the standard error. So the average of the samples is the same as the average of the population. That always stays the same in the central limit theorem. But the standard deviation gets adjusted by sigma divided by square root of n. So you don't have to memorize it, but it's right here in this formula sheet. But again, a lot of people forget to put that in there. Okay, same type of question, except now it says find the probability that her height is between two numbers, 63.5 and 64.5. So the main difference is when I do normal CDF, I don't need to use the 10,000 for infinity. I'm going to put 63.5 for the smaller number and 64.5 for the bigger number. And then the mean is 63.6, so that one will stay the same. But the standard deviation given in the problem is 2.6. But we need to divide it by the square root of the sample size. And here it's 1 again. So when it's 1, really you could ignore that, but it's just good to get in the habit. If you see a sample size, put that on the standard deviation. So now the probability to 4 decimal places is 1507. 0.1507. What if 8 women are randomly selected? Second enter, and change it to an 8. Divide by the square root of 8 instead of the square root of 1 on the standard deviation. 3795. Okay, the next couple of questions deal with section 6.7. This is something known as the normal approximation to the binomial, and they'll tell you that you're doing that. Using the normal distribution as an approximation to the binomial distribution. That's the only time you do this. In order to do it, you're kind of combining what we did with binomials in chapter 5 with all the stuff we've just learned now in chapter 6 about normals. And this approximation was actually more useful in the past before we had calculators. But even though we have calculators, we still do this. It'll only work though if this is true. N times P, which is actually the mean formula for a binomial. NP has to be greater than or equal to 5, and NQ has to be greater than or equal to 5. If either one of those is not true, you can stop immediately and click B and say the normal approximation is not suitable. So that's always your first step, is to figure out if I can even do this or not. N is 14 and P is 0.5. So this is like the binomial where you do N times P. 14 times 0.5 is 7, and that is greater than or equal to 5. And if P is 0.5, Q is the probability of failure, and it's a complement to P. So Q is always 1 minus whatever P is. 1 minus 0.5 is 0.5. Anytime P is 0.5, that's the one time Q is the same thing. So of course, N times Q is also going to be greater than or equal to 5 because that's also 7. So the normal approximation will work. I can't answer B. The answer will definitely be A. If we were doing fewer than 5, for a probability question in chapter 6, we would use normal CDF. We would do negative 10,000 to act like negative infinity. Then we'd put the 5. Then we'd put the mean and the standard deviation. Well, this problem doesn't give you a mean or a standard deviation because it's a normal approximation to the binomial. So that means you can use those binomial formulas. Go back to the chapter 5 formulas. The mean of a binomial is n times p, and the standard deviation of a binomial is square root of npq. Well, n times p, I did that already. But if you forgot, you could do it here again. N times p is 14 times 0.5. That's 7. The standard deviation would be square root of n, 14, times p, 0.5, times q, 0.5. So what you would think you would do here is you would think that you would put in normal CDF I want fewer than 5, so I would do negative 10,000. You would think that a 5 would go here for the upper limit, and then the mean is 7, and the standard deviation was that square root of 14 times 0.5 times 0.5. And I'm doing that again here so I don't get a rounded version of that. That way it'll give me the exact answer. Although it turns out on normal approximation of binomial, you don't use a 5 here. Check the textbook, they'll give you a better explanation of why it's not 5. But if you're doing fewer than 5, that does not include 5. So there's a thing called the correction for continuity. If you read about this in section 6.5, you'll see that, or 6.7, you'll see that this is a 4.5 instead of a 5. It's always off by 0.5. So if they say 5, you're not going to use 5 here. It'll either be 4.5 or 5.5. And then if I do this, this wants it rounded to 4 decimal places, 0.907. And if you tried to do it with 5, it would be off a little bit. If I redid this problem and deleted that 4.5, and made it just 5, like you think it would go, it would be off enough. 14.25, it would tell you you're wrong. So you'll need to read that. If you didn't understand that when you're doing the homework, go back to 6.7 and check how that correction for continuity works. So here's another problem just like this. N is 12 and P is 0.3. So N times P, 12 times 0.3, is only 3.6. NP is not greater than or equal to 5, so this process won't work, and I can automatically click B. The normal distribution cannot be used. That's a nice one because then you don't have to do it. The last example of this has an N of 13 and another P of 0.5. So N times P is 6.5. N times Q would be the same thing. And only when P is 0.5 are they the same. If I was doing that other problem where 12 times 0.3, if that had been big enough, then for NQ I would have done 12 times 0.7. If P is 0.3, Q would be 0.7 because it's always 1 minus it. But I didn't have to do that for the last problem because NP already failed. But both NP and NQ are good enough for this problem, so the answer is definitely not B. I can definitely do at least 5. The mean will be the same as NP, so the mean's going to be 6.5. The standard deviation would be the square root of 13 times 0.5 times 0.5. N times P times Q. The problem with trying to type 1.8 though, if you round it here to 1.8, then it'll throw the answer off a little bit. So I'd rather use the whole decimal than just a rounded version. Now here's one that says at least 5. The other question said fewer than 5. So we wanted to start at 4.5 and go down to negative infinity. If this said more than 5, I would use 5.5 all the way up to infinity. But at least 5 means 5 or more, so this includes the 5. So using that correction for continuity in section 6.7, second vars, normal CDF, my lower bound is going to be 4.5 instead of 5. The upper bound is infinity or 10,000. The mean is the NP 6.5, and the standard deviation will be square root of 13 times 0.5 times 0.5. And this answer would be 8664 if you round to, oh no, it says round to 3 decimal places, so you gotta be careful. Round to 3 decimal places, not 4, 866. Always check how many they want before you submit it. They change for some reason from problem to problem. Which of the following is not a requirement for using the normal distribution as approximation to the binomial? Clearly, NP has to be greater than or equal to 5, and NQ has to be greater than or equal to 5, so A and D are conditions of it. The sample is the result of conducting several dependent trials. No, that's the wrong answer there. We always want independent trials, and C has the word independent in it. independent trials, and it has all the other requirements of a binomial. But the key one here is dependent is definitely wrong. You never do dependent trials. So that's the end of chapter 6, the first 15 questions of our chapter 6. Now we're moving to chapter 7, and the last 10 questions are for this. These are confidence intervals. A point estimate in a proportion is how many people say yes divided by how many people are asked the question. So in the directions here they say in a poll of 920 people, X 582 said yes. So 582 divided by 920 is the sample proportion. That's what's called the point estimate of the population proportion. Round this to 3 decimal places, 0.633. Okay, then go to your formula sheet here. We're at the top right corner, confidence intervals, chapter 7. The first one is for proportions. We'll do some for means and variances later, but proportion, the main formula is p hat, that sample proportion I just did, minus e, the margin of error, is less than p, the population proportion, is less than p hat plus e. So first we got to calculate the margin of error. Capital E stands for margin of error. You get a z critical value times the square root of p hat times q hat over n. The z critical value comes from the percentage that they ask for. Here it says use a 90% confidence interval. If you click on this table of z-scores, you probably won't need this chart here because that's what normal CDF does for us. You could choose to do this if you want to do all those by hand, but it's easier with a graphing calculator to use normal CDF. But at the bottom of this table, right in the bottom right corner, here's three very common critical values. If they ask for 90%, it's 1.645. 95 use 1.96, and 99 use 2.575. This question said 90%, so my critical value is 1.645. 1.645 times the square root, I'm following that margin of error formula. Then you put in your p hat, which is this point estimate, 0.633. And then we want to do times q. Q is always 1 minus that. So if I put a parenthesis, 1 minus 0.633, that'll be what q is, close parenthesis. And if I divide by the sample size, which is this 920, that's the n, this calculation, you can type it all at once as long as you put a parenthesis around that subtraction part. Enter, this is your margin of error, rounded to 4 decimal places. 0.0261. 0.0261, that's the margin of error. Then, following the formula, the final answer is to do your p hat minus the margin of error and the p hat plus the margin of error. This gives us a range where we think the real proportion is between. So p hat was 0.633, and then you do that minus this margin of error, you just got 0.0261, and then I just hit second enter and change the other one to plus. Do one with a minus and one with a plus. And then here it says round to 3 decimal places, even though this was round to 4. 607 would be the lower limit, and 659 would be the upper limit. So I think the real proportion is between those two. So the way you interpret this is you have 90% confidence that the interval from the lower bound to the upper bound actually does contain the true value of the population proportion. This is A. That's how you interpret a confidence interval. It's how confident you are that your interval contains the true value of the population proportion. So you could think of this like with the elections right now. If one candidate, there's some true proportion of people that are going to vote for a candidate, but if we think it's between 60.7% and 65.9%, then we're 90% confident that the real percentage is in that range. Although then there's a chance that we might not be right, but in the long run we would get it right more often than we would not. So there's the answer to that one. Okay, this is the same exact question, except they don't have all the steps to fill in, but you should follow the same steps. They give me 10,000 total deaths, and 4961 of them occurred in the week before a holiday. So the p-hat point estimate is 4961 divided by 10,000, which is 0.4961. That's your p-hat point estimate. And that's needed to do the margin of error. Again, it asks for a 90% confidence interval, so I'm going to use that 1.645 amount. If they change it to 95 or 99, I could use the other two that are in the formula sheet. Times the square root of p hat, 0.4961, times parenthesis 1 minus 0.4961 will give you q hat, divided by 10,000 for the sample size. This is the margin of error, 0082. Now take your p hat, 0.4961, and minus this margin of error, 0082, and also add it on. So I'm doing one with a minus, one with a plus. So I think the real proportion is between and this is round to 3 places, 488, because 4879 would round up to 488, 504. 5043 would just stay 504. So it was the same exact problem, except it didn't ask for all the steps. I had to do all the steps myself. Based on this result, does there appear to be any indication that people can temporarily postpone their death? The only way you can answer yes to a question like this with proportions is you would need both of your answers to be entirely above or below 50%, depending which way this is going. For somebody to predict their death before a holiday or postpone it, we would want the percentage to be below 50%. Because if it's only 50%, then it's the same as just guessing. So because one answer is below 50 and one answer is above 50, then the answer is no, because the proportion could easily equal 0.5, and then it would be the same as somebody just guessing right if they're getting it right or wrong. So in order to say yes, you would need both of these answers to be below 50%. Or like in elections, when they declare a candidate has won a state on the night of an election, before the results are done, the reason they do that is both of these percentages are well above 50%. So if they're confident that the real percentage is somewhere between them, and it's well above 50%, then they're confident that that candidate's going to win more than half of the state and win the state. But if the percentages straddle 50%, then you can't say yes to your question. Okay, now we get to practice finding, well, that's the end of proportions. Now we're going to do confidence intervals for means. And once you get to a mean, there's two distributions you might use. The normal distribution is associated with the letter Z, but there's another one called the T distribution. And the difference between when you use them basically comes down to, do you know the population standard deviation sigma, or do you only know the sample standard deviation S? In mean problems, they have to give you sigma or S. Here it says sigma is known. If sigma is known, then you definitely use Z. And if you click on the table of t-values, if you remember on proportions, they had it at the bottom of that one page, and it's the bottom here too. Here's these values at the very bottom, 2.576, 1.960, 1.645. Those are those same values that we used before in that other table. And if you look at the area in two tails, if they give you 95% confidence level, then you have 95% in the middle of your graph, which means that you have 5% in the two outside areas. So the area in two tails is 5% anytime they give you 95%. And if you can use Z, which you can use Z anytime sigma is known, then you get to go straight to the bottom of this t-table. So the critical value would be right here, 1.960. And that would be choice A. Yep, okay, wait a minute, I messed up. Let me read the problem. I made the classic mistake. Find the critical value, z or t, or state that neither can be used. That was what I didn't check. Was sometimes you can't do z or t because you have to go through those two things of the central limit theorem that I said. Either they have to tell me that the population is normal, and here it says the population appears to be very skewed, so it's definitely not normal. Or number two, the sample size has to be greater than 30, and it's not here, it's 21. So I made the classic mistake of not reading the whole question. This would have been 1.96 if either they would have told me that the population was normal, or if they would have given me an n bigger than 30. But since they didn't, then I have to click E. It's neither the t nor the z. Neither normal nor t applies here. And that comes directly from the central limit theorem. In order to do z or t, the central limit theorem has to apply. And you either have to know somehow that the population is approximately normal, or, which they usually just tell you in the problem, or you have to have an n over 30. If both are untrue, you click E, that you can't do anything. Now in this next one, 19, now they say n is 300, so that is greater than 30. The population appears to be skewed, so it's not normal, but that's okay. The central limit theorem will still cover me. As long as n's over 30, I don't care what the shape of the population is. My sampling distribution will still be normal. Here it says sigma equals 17, so we do have sigma given, then we have to use z for sure. It's definitely z now. It won't be t and it won't be neither. It's 95% again, so this will be the answer I thought the last one was. This will be the 1.96 answer. And these couple of questions here, they're getting you to practice this finding critical values for means because it's done a little differently than proportions. What if I want a 99% confidence level, n is only 22, which could be an issue. Sigma is unknown, so that means we definitely cannot use z. But even though n's is only 22, the question says population appears to be normal. So that saved me. The central limit theorem will apply because they said that, even though n's under 30. So I can still do this problem. Sigma's unknown, so that means I use a t distribution. The difference between z and t is where you go in this t table. If you have a z when sigma is known, you automatically go to the bottom here where it says large degrees of freedom, depending which column you're in. If you don't get to use z, if sigma is unknown, then all you'll have is s, and you'll have to use the t distribution, and that's when you use degrees of freedom and you're somewhere inside this table, not all the way at the bottom. So you find where you're at by figuring out what percent is given, 99%. A confidence interval is always the area in the middle. So if there's 99% in the middle, 100 minus 99 is 1. There would be 1% or 0.01 area in two tails. So I look at the very first column, and I go down this column. Since n is 22, the definition of degrees of freedom is it's n minus 1. n's 22, so I go to 21 degrees of freedom in this very first column where it's 0.01, and the critical value would be 2.831, which is choice B. So question 18, 19, 20, they're getting you to practice getting the critical value because that's one of three steps for doing confidence intervals of means. They actually have another one here. Confidence level 99%, n's 23. Now sigma is known. Population is normal, so I can do this problem because the population is normal. Sigma is known, so that means I'm getting to use z. And that means I go straight to the bottom of one of these columns. 99% in the middle means that I have 1% on the two outside areas. So I go straight to the bottom of the first column. 2.576 would be the critical value, which is A, 2.575. Some books round that up to 6, some leave it 5, so it's not a big deal if the last digit's off by 1. Okay, now we're actually going to calculate a confidence interval for a mean, which is using the formulas. Here's the one we did already for proportions. The ones for means are very similar. You get an x bar, a sample mean is like a p hat. You calculate your margin of error using the critical value, the thing we were just practicing for the last 4 problems. But on means, it depends whether you're doing z or t. Is sigma known? Do z. If sigma is unknown, you'll have s, and then you use t. With proportions, we never had to worry about that. It was automatically z, but means you could have z or t. So another thing that can happen too is you might be able to, here it says use technology to get this answer. Now if they ask for all the steps, like if they ask you what's the critical value, what's the margin of error, and then what's the answer, then this wouldn't help you so much. But if all they want is the answer, you can do this in your calculator. Go to stat and over to tests, which we're going to do a whole lot more starting with chapter 8. Stat and tests, starting with number 7, they have a bunch of intervals, and that's what we're doing here is confidence intervals. So first I have 98% confidence, n is 41, x bar is 2, and s is 3.2. So it says, assume that the population is not normal. That's normally a bad thing to say that, but we're saved by the fact that n is over 30. So we can do this problem. Now we have to decide, since it's about means, we've got a mu here, not a p. Mu is for means. Are we going to do z or t with a mean? We have to decide that, and it's decided for us by what was given to us. S is 3.2. S is the sample standard deviation. You have to have sigma in order to do z. So we're going to do t because sigma is not known. All we have is s. So I can click the t interval. I want to go, input is either data or stats. You put data if they gave you all the answers and you had to type them into list 1 or something. So here you can move it over to stats. While it's flashing on stats, click enter. Then you just fill in all this information they're giving you. So the problem said that x bar was 2. So go down here where it says x bar and put a 2. S is 3.2. N was 41. And the C level or confidence level is 98%, but you got to change it to a decimal, 0.98. And then calculate. And this will spit out the 2 answers we're looking for. And they're doing it here in interval notation with one answer, comma, another answer in parentheses. That's from college algebra. You can also do this in inequality notation with the double less thans. It really means the same thing. Put the negative 112.3 first. And then put the 116.29 second. So I think the real mean for the whole population of how much weight people lose on this diet is somewhere between negative 112 and positive 116. So that's a bad sign if the interval's that wide, because that means people might gain weight. Negative in this situation would be gaining weight. So if you're gaining 112 pounds on a diet, that's not a good thing. Okay, I must have had a typo somewhere. Okay, t interval. Oh yeah, see it says I put 302, but it was supposed to be 3.2. So yeah, that didn't seem right to have such a wide interval. Okay, so I just have a typo here. Stat, and again, I went a little too fast here because I'm trying to keep this video short. Whenever you're using this technology, this is a danger that could happen to anybody where you type it in wrong and get the answer wrong just because you typed it in wrong. So I would always, if I was taking a test, after you type them all in, go back with your finger and check that you typed them in right. I had 302 here, not 3.02. And that's what caused the answer to be way off. And on a test, you're not going to know if it's right till you submit the test. So it's actually 0.85 round to 1 decimal place. So 0.9 and 3.1. 0.9 and 3.1. So that's better, because that means on average people are losing either 0.9 pounds or 3.1 pounds. We think the real average weight loss is between 1 and 3 pounds basically. Is the confidence interval affected by the fact that the data appear to be from a population that is not normally distributed? Is the confidence interval affected by the fact? And they say no, because the population resembles a normal. What? No, it doesn't. No, because the sample size is large enough. And that's the answer here. It's not affected by, we were able to do this because n was over 30. That comes from the central limit theorem. And you either need to be knowing that the population is normal, which it wasn't here, or you have to have an n over 30. If your n is over 30, it doesn't matter that the original population is not normal. that's okay. So the confidence interval is not affected if n's large enough, and it is here. Anything over 30 is considered large enough. Okay, so now we're going to, there's two main things left. Right below that on the formula sheet, we've done a confidence interval for a proportion, one for a mean. There's one for a variance or a standard deviation, which is last. But another thing you can do in chapter 7 is down here at the bottom. You can find how large of a sample, what should n be, so that you get a certain margin of error. How many people should you question under certain conditions, in other words? So what they give me here in this problem is IQ score is designed so that the mean is 100, standard deviation is 18. Find the sample size necessary. How many people should I question? So I can estimate the mean IQ score for students so that it can be with 90% confidence. And we want the sample mean to be within 3 IQ points of the true mean. Within, that's a magic number that really means the margin of error. The margin of error is plus or minus. We want to be within 3, so that's the margin of error. So in the formula, there's 3 numbers you plug in. They need z critical value times sigma standard deviation divided by the margin of error, capital E. That's the margin of error. That's that 3 in the problem. And the standard deviation was given in the problem. The only thing that's not given is z. But z is that critical value that is at the bottom of those t-tables. And remember the 90%? If you go to 90% in the middle, that would leave 10% on the outside, go straight to the bottom of the table, and you'll see there's a 1.645 there. So this formula goes the z critical value, 1.645, times the standard deviation, which is 18 here, divided by the margin of error, 3. Once you get that, you square the whole answer. The formula has a square in it. So 97.4. Now, the one thing about sample size is it's the number of people you're going to ask a question to. So I can't ask 97.4 people a question. You would think that the answer would be 97. But it turns out if you get any decimal at all on a sample size problem, you always round up. And it even says it here, round up to the next integer. If you round down to 97, you will not have 90% confidence like the question wants. You would have like 89 point some percent confidence. So if you want 90% confidence, you have to have 90 or more. It can't be under 90. So it's better to have a little too much than a little too little. So the required sample size here would be 98, not 97. Would it be reasonable to sample the number of, would it be reasonable to sample this number of students? So in other words, is it an impossible task to go out and ask 98 people a question? It will take a while, but that's not an impossible task. If this came out to like 5,000, you're probably not going to want to go around asking 5,000. So yes, this is reasonable because it's a fairly small number of people to ask a question to. Many surveys have more than 98 people in them, so this is not an extremely large amount. And that's what's good. Once you know you need 98 people, then you can stop asking after that. When all these political polls have their surveys and results, they're not just asking people till they get tired of asking. They do this calculation in number 23, and they know exactly the amount needed. Okay, the last thing is, how do you do a confidence interval for standard deviation or variance? The formula sheet has it for variance, but if you need standard deviation, all you have to do is square root it. Standard deviation is always the square root of variance. So I'm going to follow this formula right here, but with square roots on it. First of all, the degrees of freedom is just like it is for the other problems. Since n is 24, I'm going to have 23 degrees of freedom here. Okay, this table is different because with variance and standard deviation, we're using the chi-square table, not the t-distribution. So the way this is done is you take the percentage that they give you again, 99%. That would be the middle percentage. So that means there's 1% on the 2 outside areas. But our 2 outside areas here are different. They're not equal. So I don't get to just say that there's 1% in 2 tails. I really have to worry about how much is there in 1 tail only. And if there's 1% in 2 tails, there would be 0.005 in 1 tail. That's the very last column here next to degrees of freedom. This table's cut in half. The 5 columns on the right and the 5 columns on the left give you 2 different critical values, a left critical value and a right critical value. It's easier to do the right one first because you get that percentage by doing 100 minus 99 and then cut that in half. So half of 1% is 0.005, and I would go down to 23 degrees of freedom. But the question wants the left one first here. So it's easy to get the left one once you get the right one. The right one is down the very first column on the right, 23 degrees of freedom. So that means the left one is on the very first column on this side. All the way down to 23 degrees of freedom, 0.9260. The right one is the very last column at 23 degrees of freedom, 44.181. Oops, I didn't type that right. 44.181. So what I always do is I find the right one first. You'll use one of these 5 columns. Go down to the degrees of freedom for that. The other answer is in the same row, the same degrees of freedom on the other half of the chart. And it's the same number of columns over. If you go 3 columns over this way, then the other one's 3 columns over that way. And the left answer is always on the left of the table, the right answer is always on the right of the table, even though it's easier to find the right answer. Okay, then we're going to plug these critical values into the formula. The formula wants the n minus 1, which is really the degrees of freedom, times s squared over the right critical value first. And if I do it with a square root, I'll actually get standard deviation instead of variance. So we had 23 degrees of freedom. S is in the problem. S is 0.22. That's the standard deviation. But in the formula it gets squared. And then you divide by your right critical value first. You would think you'd do the left one first, but it turns out you do the right one first. 44.181. And don't square that number because the table has already squared it. You might get confused on the formula sheet. S is squared and this chi-square on the right is squared, but that's all those values in the table are already squared. So you do have to square the s, but you don't square the chi-square value. It's already squared. So the lower standard deviation answer would be this, rounded to 2 decimal places, makes it 0.16. And then you do the exact same thing with the right critical value. So I just hit second enter, with the left critical value. The left critical value is 9.260. So just type right over this one with that one. 9.260, and I can delete the 1 that's not needed. 0.35 rounded to 2 decimal places. So I think the real standard deviation is between these 2 values. And then you get to do the exact same thing in 25, just another practice for this. Okay, so find a 98% confidence interval. And we have 70 cookies here. The sample size is 70. So the degrees of freedom would be 69, and we have 98% given. So I always do the right one first. It's easier to get both of them that way. There's 98% in the middle. Minus from 100 is 2%. But then you have to cut that in half to 1%. 1% is 0.01, so it's the second column from the right. So the right-hand critical value is the second one from the right, and I would go down to 69 degrees of freedom. The problem is, once it gets past 30, it stops going by 1s and it starts going by 10s. So it jumps from 60 to 70. I can't do 69. You would think to do 70 because 70 is closer to 69, but you don't. Again, it's not good to go over, so we have to go back to the upper one, the one closer to the top of the chart. Even with 69, I go all the way back to 60 degrees of freedom, the 0.01 column. The right-hand critical value would be this, 88.379. 88.379, so that's the denominator of the calculation. So it's square root, degrees of freedom 69. I use 69 here even though I use 60 in the table. And then S is in the problem somewhere. Standard deviation is 2.87. Then I divide by that number in the table. At 60 degrees of freedom, 88.379. So there's the lower one, and then I can hit second enter and type over this 88 with the other critical value. And it's easy to find it now that I've got this one from 60 degrees of freedom, 1, 2 from the right. So go to 60 degrees of freedom here, 1, 2 from the left. 37.485. 37.485. 37.485 is the other critical value. And the reason the right one goes first is because when the denominator is bigger, the answer is smaller. When the denominator is smaller, the answer is bigger, and they always like confidence intervals to be listed with the smaller number first and the bigger number second. So the problem wanted it rounded to 2 decimal places. The smaller answer is 1.49. And if you do the bigger one first, that's fine. Just make sure you put the smaller answer in first. And the bigger answer is 2.29. Okay, so wait a minute. Okay, let's see. The standard deviation is 2.87. Do I have a typo? Oh yeah, I put 2.84 for some reason. Standard deviation, usually when it's wrong, it's a typo. So I'm going to hit second enter twice. So I can change that 2.84 to a 2.87. And then I'll hit second enter once. And I need to change this critical value to 37.485. So it actually should have been 1.50. I had 1.49, so I was just barely off. 1.50 and 2.30. So if you get even the slightest typo, it was 2.87 and I had 2.84 for some reason. That's all it takes to throw that off slightly. Nope, but something else is still wrong with it. Let's see, where's the degrees of freedom? 70, so it should be 69, yeah. And maybe I'm just reading the table wrong because it's so small. Where's my table? Degrees of freedom. Maybe that's, can't tell if that's 88.379. 37.485. I'm pretty sure I have those. Well, just to save time here, let me just see what they say the answer is. Yeah, I did something wrong on this one. Sometimes you can come up here and see what they're doing. Oops, I guess not. Okay, well anyway, I'll check that one, but I'm running out of time here in this video, so I'll check that one and email you what went wrong with this problem. But at least you got everything here to help you with some calculator shortcuts on the test, and as always, send me any questions that you have. And don't forget, this formula sheet can be very helpful too. And then I'll be doing one more video for chapters 8 and 9, and then we'll do one for the final exam as well.